Hello, my name is Pitt Volmers, and this is the GVSU 2021 Senior Project Overview for Team 17, the TNT Tools Hook Handle Bender. The purpose of the senior project is to bend the handle of a manhole cover hook to the design specifications. The hooks are to be made from a 5/8 inch 4140 steel hex bar. The product's lengths range from 24 to 36 inches, and there's two different types of hooks, a straight hook and one with a 90-degree twist. This is the process that TNT Tools currently utilizes to make their hooks.
Go in with it, stop here. That'll be my first bend.
After this
I'm going to flip. I'm going to line it up right there with my mark. I'm going to lock it in place. This is going to come around my backside.
As one can see, the machine has a significant
So I got my first side of it. Bring it in there to stop. Lock it in. Bring it back across.
Once
okay, so now see how it's kind of offset? So then I'll take it in here. I'll kind of get it straight. And then I kind of look at it. It's kind of like this. Alright, so then I usually take this.
The main issues that the sponsor is concerned with regarding their current process includes the safety hazards that the operator faces in handling red-hot metal between stations, the multiple exposed pinch points, and the large swing path of the moving components during the bending process. Secondly is the furnace itself, having significant energy costs and large byproducts of heat, as well as limiting the cycle time. And lastly, that two different rotary benders machines are required in addition to hand adjustments that the operator needs to make afterwards. The key specifications that were agreed upon with the sponsor in the initial stages of this project are as follows. Bend the handle without heating the metal. Meet print dimensions and tolerances, specifically maintaining a maximum handle gap width of 0.05 inches. Include pinch point guarding and other operator safety features. Stay within a constrained budget of nearly $22,000 and have the machine footprint be no larger than 4 by 6 feet. We performed a series of tests on the current machines used at TNT Tools to establish a baseline for our machine's performance. They are bend testing, pressure testing, as well as twist testing. The purpose of the bend testing was to investigate whether it was possible to successfully bend the bar stock without heating it up first. Additionally, we wanted to determine the bend speeds and angles that would cause the material to fracture. Lastly, we wanted to quantify the amount of material springback error that would occur between the desired angle and the final measured angle. From these tests, we concluded that it would be feasible to perform these bends without the use of applied heat. At the default machine speed of 10 RPM, fracture occurred at a roughly 75-degree bend angle. However, we were able to significantly mitigate the risk of fracture by bending at a reduced speed of 1 RPM or less. And lastly, there was a springback error of approximately 7% between the bend set point and the final measured angle. The pressure testing was performed to quantify the forces and torques required to bend the stock. This would provide us with critical information to use during the component selection process. The machine currently used at TNT Tools is a hydraulic rack and pinion type rotary bender. We knew that the hydraulic cylinder used has a 4-inch bore. Additionally, we knew that the pinion was 5 inches in diameter. Using the pressure gauge attached to the hydraulic system, we observed a peak pressure of 500 psi that was maintained throughout the duration of each bend. Using the information, we were able to calculate the forces exerted from a cylinder, as well as the resulting torque exerted by the rotary table, accounting for a hydraulic efficiency of roughly 90% and a factor of safety of 1.5. The force and torque were 6,981.3 pounds and 2,181.7 foot-pounds, respectively. Finally, the twist testing was performed to evaluate the risk of material fracture, as well as the degree of material springback. The severity of each was expected to be greater than what was observed during the bending testing, and additionally, we wanted to determine whether more or less torque was required to perform the twisting versus the bending operation. And as expected, the average material springback error was much greater in this case, being 15% as opposed to 7% during the bending process. However, the twisting operation was performed using nearly the same amount of torque as the bending, at 2,181.7 foot-pounds of torque. Unfortunately, the testing apparatus became damaged during testing, and regardless of this provided us valuable information regarding the die material selection. Additionally, undesirable die marks were left on the test parts, which indicated that a change in die geometry would be required to satisfy the sponsor's specifications. After achieving a proof of concept through testing, the design phase was kicked off. This render here shows the final design of our concept for the hook handle bender machine. To begin, the machine will be loaded with 5/8 inch hexagonal steel bar. The machine will then perform a compound bend in the clockwise direction, followed by a counterclockwise bend. Notably, overbend allowances are made in both directions to allow for cold bending material springback. Next, the bar will be loaded into the twisting assembly, where a 90-degree twist will be made to account for variation in final product geometry as desired. As mentioned previously, there are a number of advantages to the chosen concept. Foremost among these advantages is team member safety. For this design, all moving components are fully enclosed within the machine during operation times. Also, the inherent simplicity of the design allows for all rotational torque to be transmitted from a single servo through a gear reducer to the slew drive, which acts as the workhorse of our design. Additionally, the design facilitates important adjustability in bending parameters, specifically rate of bend, degree of overbend, and bent bar stock diameter. As we walk through the critical components of this design, we will dive into 3 areas to focus on, namely the external fixed die, the internal fixed die, and the rotary die assembly. Collectively, the interaction of these 3 assemblies create an environment which determines the tolerancing and dimensions of the final product, providing sufficient fine-tuning capabilities if adjustments need to be made. First, we'll dive into the rotary die assembly. Pictured is the rotary table, which drives the bending motion of the hexagonal 4140 steel bar. Most notably about this component is the hole pattern. In order to facilitate necessary adjustment for cold bending material springback, the rotary plate was designed with 8 possible configurations. Holes A1 through A8 and A9 through A16 work in pairs, with each pair of holes creating a uniquely calculated radius of bend around the central rotating die. Each radius of bend correlates to a percentage of overbend in the hexagonal steel bar, ranging from 3% to 10% overbend, which allows the machine design to account for springback inherent to cold bent products. Also pictured in the top left of this slide is the central fixed die. This die is designed to hold the part in place while creating the desired internal radius for the handle of the final product. Next, we'll look at the external fixed die. This assembly provides a hard stop which works in tandem with the rotating and fixed assemblies to meet the overbend requirements of the final product. In the drawing to the right, parts 1 and 3 sit below the main table face, while parts 2 sits above the table to interact with the bending moving bar. As with the rotary assembly, there are 8 possible locations of adjustability. One important aspect we had to keep in mind were the shearing of components. The 3 critical components in this case are the twisting base bolts, the large bending die, and the small bending die. The twisting base bolts will see a large shear force when the handle twisting operation is performed. Similarly, the large and small bending dies will see large shear forces when they are in contact with the steel bar during bending operations. Calculations were made, and it was determined that the components had a sufficient factor of safety as well as endurance limit. Another important aspect to consider in the design of the machine was the required torque. Calculations were performed based on testing results to determine the torque rating we would need for various components, namely the servo, gearbox, and the slew drive. The details on this slideshow indicate the chosen component ratings. The equipment used to control the rotary bender are a Unitronics PLC, servo, and servo drive. By using all Unitronics components, the interfacing between the parts is much simpler. The simple communication between the devices greatly reduces the chance for error when creating the program. The PLC contains a 5-inch diameter Hmi screen, which will be used for maintenance and parameter adjustments. There will be 2 sensors which are used to determine whether the machine will be performing the bending program or the twisting program. The sensors are induction sensors and will sense the part at certain locations on the machine. They'll be placed so that it's impossible for both sensors to see a single part at the same time, and there are also buttons located near the operator handle which will start the program chosen by the sensors, and an emergency stop button which will cut power to the machine if pressed, halting the current operation. Indicator lights will also be located on the machine, which will indicate if the bending or twisting sensor are seeing a part. If the machine reads a part at one of these locations, not both, the ready light will be lit. The other light is for error, which will activate under certain conditions, such as both twisting and bending sensors reading a part, the safety interlock being disconnected, or the e-stop being engaged. For the basics of the program being used in the machine, a state diagram was made to show the options the machine will have when running. The initial and default state is state A, idle. Anytime the machine is powered on or finishes another state, state A occurs, keeping the machine idle and preventing the servo from activating. State B is a bending state, which occurs when the bending induction sensor is activated and the ready button light indicator is on. The machinist then pushes the start button and state B occurs. Again, after state B finishes, the machine returns to state A. State C is the final state and is the same as state B, the only difference being that the twisting induction sensor must be active and not the bending sensor. On the electrical cabinet, there is an Hmi screen which will provide options for the operator to use to adjust the twisting and bending values. This screen will also allow for maintenance mode to test the machine. The challenges that we encountered in this project that were the most difficult were fine-tuning the code of the servo to the optimal bend angle and bending rate to achieve the best handle shape. Since some components were machined in-house, the stock available had some rust present. To ensure that this does not damage the structural integrity and to extend the service life of the machine, the majority of the components were black oxide coated. The machine components that were custom made for our products were also delayed for nearly a month due to global shipping delays.